Right. So this is going back to our triangle and all the rotations and permutations of it, or the covering operations, the symmetry operations of it. So we can compute the character table. Go ahead and do this. Number of classes. There's the identity, which forms a class. There's rotations, which forms a class. And then there's the permutations, which form a class. And it's, I mean, I guess you can, in some sense, see that those things form classes among themselves because one permutation is similar to another. Transposition. Yeah, so transposition is probably a better word. Yeah, so the relabeling of two indices, but transposing them. That forms a class on itself. And then the rotations, which are pure, like, so the permutations that you can obtain from rotations would form a class themselves. Yeah, cyclic permutations is a good way to say it. So those are the three classes. Class 1, which is the identity class, it only has one element, so I just have a 1 there. The second class, which I'll take it to be the transpositions, it has 3 elements because we have 3 transpositions. And then we have just 2 rotations, 2 pi over 3 and 4 pi over 3. And that has 2 elements, and I'll call that the third class. Right. Number of ear reps equals the number of classes, so then I am going to have 3 ear reps. One of them is just, well, I can fill this in, right? I know that. So this one would just be the identity ear rep, so mapping everything onto 1, all the group elements onto 1. This one, I guess you can think of would be the parity mapping, where I take each group element and I map it to its parity, so plus or minus 1. And so that also has dimensionality 1, because it's just a scalar. And then the third representation is the 2-dimensional one that I write it as a matrix that has a rotation and also a transposition in it, right? So I could write the rotations in matrix form, but I could also write the transpositions in matrix form. And then using those 2, I could take products to generate the rest of the group. But anyways, that's a 2-dimensional representation, so I get a 2 here. So these are the elements that we have to do a little bit of work for. We don't know them, so I'll just call them A, B, C, and D. All right, so I use the first 2 rules to get this and that. I need to use those other 3 rules to get the rest of these. Typically, if you can find integers that satisfy all this, then they are the actual characters themselves. They don't necessarily have to be, but if it works out, then typically the integers will give the answer. So I'm going to assume that A, B, C, and D are integers. And then I can use rule 3 and this row right here. So that's the orthogonality theorem right here. And if I write that out, so I just need to basically take the squares of all these elements and add them, but weight them by the number that shows up right here. That'll give me 4 plus, so 4, 2 squared, and then plus 3 times c squared, and plus 2 times d squared. Since I'm doing the same row, that has to add up to the order of the group, which is 6. This tells me that c has to be 0, right? Because d is an integer, so its square is a positive number. So if any number besides 1 is here, and this isn't 0, then it's not going to work out. And not that it matters too much, but I guess this would also tell us that d has to be plus or minus 1. So now I can use 3 again, and then I'll use these 2 rows. Rule 3 except with this row and that row. And so in that case, I would get 2 times 1 plus 3 times c plus 2 times 1 times d, so 2 times d. This is 0 because I found c is 0, and this has to equal 0. So from this, right, you can easily see that d is equal to minus 1. All right, so I'll use 3 one more time. But this time I'll do it on sigma 2, or not sigma, gamma 2 and gamma 3. I'll get 2 plus 3 times A times C plus 2 times B times D. This is 0 because C is 0. D is minus 1. Right, so this would give me 2 times 1 minus B equals 0. So B has to equal 1. And then the last rule I'll use, rule 4 over there. And for this one, I'll use this column. 1 plus A plus C, C 0, which is just 1 plus A. That has to equal 0. I think I messed something up here. Oh, my bad. I'm sorry. I'm using this column and this column. In that case, this should be 2 times C, right? But in any case, it's still just 0. From this, I get that A is equal to, so now I can fill this out. Minus 1, 0, B is 1, and D is minus 1. So now my character table is filled out. Use all this magic. We've got the character table, and then we could go back now and compute, without going through all I went through in the beginning, to compute the projections on the invariant subspaces. Right? We could use this character table to construct the projection operators, and then we know how to operate on an arbitrary function with them. The value in doing this and all these rules. That was all I had. Was there any questions on anything?